Hello and welcome back to differential equation. This is the revenge of substitution methods and exact equations, which means 1.6 part 2. And in our last class, we talked about substitution method. Started kind of rocky, if I remember, because I wanted to use something else other than the standard y over x. Didn't go that well. And we worked out a couple of examples of this method. And I asked you guys to work on problem 14 or homework and promised that I will finish off this problem today. And then after that problem, we have the exact equations to cover. So we'll deal with that after this. So since you are all logged on to, well, not all of you, you're still coming in slowly, but between the YouTube and the Zoom, we do have, I guess, enough to start the class. I will remind you the homework and all that good stuff. Make sure you follow those due dates on MyMathLab for homework. And I'm going to start working on this problem. So we have the differential equation, which says y prime plus x equals to the square root over here. And we learned last class that our differential equations need to be y prime equals everything else if we are to have some hope of solving it using the substitution method. So once we subtracted x and divided by y to get y prime alone, we came up with this method, right, where you substitute x over y this time rather than y over x. And I asked you to try the top one first, and if that didn't work, then work the one on the bottom. So let's try the one on the top. Now y prime is going to be the quotient rule, right? And the quotient rule would have a u square in denominator, right? And it will have a ux prime. Well, that's one, so just u minus ux. No, u prime x. There we go, much better. And now we plug all of these in and see if we can solve the problem. So to do this now, I am going to replace u minus u prime x over u squared equal to the square root of u squared plus 1 minus u. And let's see. I have that x there. Okay, that's all right. We're going to try and see if we can somehow simplify this to the point where we can just use separation of variables, obviously, and go from there. So probably I'm going to multiply both sides by, would that work, u squared? Well, I guess I need to separate this. So let's see if we can put all of this together. So u squared, so that's going to be u minus u prime x is equal to u squared square root of u squared plus 1 minus u cubed. And then I'm going to subtract u. So that's negative u prime x equals to u squared square root of u squared plus 1 minus u cubed minus u. And divide everywhere by negative x to get u prime alone. Well, actually, do I have to do that? I can just use the... This is going to be a living nightmare to solve. Negative u. So write this as negative x du dx. is equal to all of this mess here. And then separation of variables would give us that du over this u squared square root of u squared plus 1 minus u cubed minus u is equal to negative 1 over x dx. Now left hand side is easy, it's just negative L absolute, what, ln absolute x. So negative ln absolute x is the right hand side, it's very easy. The left hand side integration looks like it's going to be more challenging than that, or not. Let's see. I mean, I have this expression which I can bring on a side and try and work out. I have this negative u cubed minus u, where I can factor out negative u and get u squared plus 1. And that's awesome because I can then factor that, right? So now I have du over u squared square root of u squared plus 1 minus u squared plus 1 equals to, I'm just going to put here negative ln absolute x plus c and be done with the right hand side. So on the left I can still do some work. Can I use substitution here? No. Or maybe I can. Let's see. If g is equal to u squared plus 1, right? If this is the case, I mean, there is rationalizing. There are like 1,000 things that we can do. Well, not 1,000, but you know. Well, let's see what the dg is going to give us. That's a 2u du. So I need u on top. And if I do that, if I put, so there should be an integral sign in front, right? That du. So I need a half over here and then a 2u on top, which would make this into a cube and this into a square because I had to multiply top and bottom by u to have enough of these. And now this is me trying. I have no clue how to solve this. These problems are not easy, not cheap. So now on top I just have my dg, and on the bottom I know I have to get rid of all of the u's, but let me still have u cubed root g minus u square g. And yeah, this is not going to work because now this u squared will have to be 1 minus g to go in there. And then what I'm going to go for a cube, right? Because u is going to be a square root of yeah, this is really bad. I don't think this is the way to solve it because this integral on the left is a terrible one. I'm not going to remove this from my notes or erase it because we need to know, right, what we tried and didn't work. Maybe I made a mistake somewhere and it actually works. I don't know. I'm gonna do a quick check over here. So subtract x on both. First of all, verify the problem. So y prime plus x equals to square root of x squared plus y squared. Good. Now we subtract x on both sides. That's minus x. Then we divide both sides by y to get y prime alone. That's important for substitution problems. When y goes under the root, it picks up a square, so it becomes x over y squared, and then y squared divided by y squared is 1. And then we have x over y. So both are x over y, and we make that into a u, and then we solve it for y, where you get x over u. And then we go and do the derivative. So we have a quotient rule. And for this, we do the square, you copy, the derivative x is 1 minus x times u prime. Good. All right, so now that goes in y prime, u minus u prime, u squared, and then u squared plus 1 minus u. Good. And then I multiplied by u squared. Yeah, this looks like it's good, but then it just didn't work out. So what I'm going to do is I'm going to start the problem again and use a different substitution here, right? And if that doesn't work, I'm going to stop wasting time and then solve it at my own time rather than wasting class time, and then just present you with a solution in next class or whatever. But what I want to try next is I want to try, so, oops, try again. So I'm going to try over here and have this whole mess here as a u. So I'm going to say, oops, let's go orange. U equals x over y squared plus 1. Because that's going to kill the plus 1 in the derivative, and you know, there are things we can do. So we solve this for, oh, but that's going to have a y squared. It's going to be terrible. All right, so y minus 1 is equal to x over y squared. So x over y is plus minus square root of u minus 1. Let's just try with a positive one, even though should be plus minus. But I'm just going to take plus to see how far we can get with this. And then from here, y is equal to x over the square root of u minus 1. So you see that now it's different than before. It's harder, clearly, but it's going to give us different algebra, and then hopefully, you know, we can do something from there. So we need the derivative, which is the y prime. Square the bottom, we just get y minus 1. Copy it to the top, which is u minus 1, derivative x is 1, minus x times, ooh. Oh no, that's the derivative of this one. And the derivative of this one is 1 over 2 root u minus 1. Okay. Multiply everything by the 2 root top and the bottom. So we're going to get, so over here, we're going to say times 2 root u minus 1 and times 2 root u minus 1, because we want to get rid of the double, fraction, right? So the bottom is going to be 2 u minus 1 to the 3 halves, because there is 1 plus half is 3 halves. Now on top, you're going to get 2u minus 1, because root times root is this, and then just minus x. Okay, this might be better. I don't know. We'll see when we plug everything in. So now bring that in there. That goes there. This puppy here is just u. And we have the x minus y from here as a root of u minus 1. So the new problem looks like this. 2 u minus 1. Oh, where's my derivative? Where's my derivative, guys? So take the derivative here, that's squared. Then the root of this one, oh, right here. This is u prime. So this is going to be u prime. Okay. Because you have to have your derivative somewhere. Okay, cool, cool, cool. Minus xu prime divided by, that was a chain rule from Calc 1 that I failed. 3/2. So that's your y prime. On the right hand side we have a square root of u minus x over root u minus 1. There we go. Whew. Nice. This is one spicy problem. Multiplying both sides by this, which is the common denominator, should actually kill all the fractions. I think so. So the entire problem times 2u minus 1 to the 3/2. We are left with 2u minus 1 minus xu prime equals 2 root u minus 1 3/2 minus, this is going to stay 2x u minus 1. Because a 3/2, one of those halves is cancelled with the denominator. So 2/2 stay, which is just 2 over 2 is 1. So u minus 1 to the first power, and then the 2 and then the x. Okay, cool. And now, can we separate this? I think we just made it worse, actually. Well, clearly we have to move this one there. Yeah, I don't think this is separable now. Negative xu prime is equal to 2 root u minus 1 to 3/2. Looks like I will have to meditate on this one to find proper. I mean, it could be double substitution. It could be, let's see. So y prime, when I divide by negative x, we get negative 2 root u minus 1 to the 3/2 divided by x, minus 2 is gone, so this is just a u over here. I mean, sorry, plus, because of the negative x is gone, so it's just 2u minus 1. But over here, I have plus 2 is gone, u minus 1 over x. And I can put the first and the last term together. So u prime is equal to u minus 1 minus 2 root u minus 1 3/2 given over x plus 2u minus 1. This doesn't look separable to me. Right, this is your du dx. So unless I made some mistake somewhere, this doesn't look separable. This is, yeah, it's a lot of algebra. It's not even calculus, it's just, shoveling terms around. As I said, substitution method is the toughest of all of these methods here. It takes most, tries and fails. I mean, that's what the life is, right? The best things are always the ones that you failed at many, 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 many times, and then you want to find a solution, then it's actually like, yes! And pretty much the stuff that you get on a first try is meaningless, and just, pretty much anyone can do it, so who cares? So you should be on the lookout for cool problems like this, and then spend insane amount of time solving them, because, they're the most fun. I will, because now I don't want to waste the whole time, the class. I learned my lesson a couple of semesters ago when I literally spent 3 hours in differential equation over 3 different lectures in, increments. working out the same problem a couple of times. If you go back in my lecture notes, you're gonna find that problem. Yeah, I literally spent 3 hours working it out. No, sorry, 3 attempts, probably more than 3 hours, um, in over 3 lectures, I think. So 3 attempts. Some of the problems in differential equations are just a whole mess. I don't want to spend the entire day figuring out one problem, which, as you can see, is not pleasant at all. I am going to figure it out because I love playing with these puzzles, and then I'll present the solution the way I found it. I'll try again. What I didn't try yet is u equals y over x, where, you know, these things would be 1 over u, right? So that will make a 1 over u there. I haven't tried that yet. That could work, you know, and just solve these problems in 3 lines. But I really don't want to invest any more time. So I'm just going to put a note here. Try u equal y over x, where x over y will transform into 1 over u. That could be the solution instantly, right? So, and we don't know these things until we try. That's why, you know, the best people, students in mathematics and everyone else who does mathematics, are those that actually persist and not give up on a first try, say, oh, this is too complicated. Because, you know, all of the good things are complicated. Just, you know, take a look at successful people, see how many failures they had. Look at Musk's SpaceX and how many failures he had. Having failed attempts, just like these two were complete failure, it's okay. That is the process of learning. So all I'm going to say here is try again. And I will try again with a different one until I find the solution, because that's what the fun of doing this is. And obviously it's important to figure these equations out because they give you solutions to stuff that it's meaningful in engineering and everything else. Now, since we don't have, right, a whole day to work on this one example, I'm just going to stop there and work on it later. And I'm going to ask those of you interested, obviously, to work on this problem as well, because I told you what other thing you can try. I'm going to focus now on exact equations, because I can't rely on the fact that, oh, you learned this in Calc 3. Those of you who did take Calc 3 learned this. Whether you remember it or not, that's on you. But I know that the vast majority of students in differential equations did not take Calculus 3, therefore I have to teach it from scratch. So it's going to be exact equations from exact equations. So we're going to have now the situation. Okay, I have, just give me 1 sec, I have to close the door. All right. Yeah, teaching from home when everyone is there is a little bit different. I do want this on a record. This idiotic government we have is just out of control with the closure anymore. So it's very difficult to do anything, and I really don't care what anyone else thinks. It's just get them out of the office and get the normal people in. At this point, it's way. Anyway, I'm talking about the state government, of course. Let's go with exact equations. So you guys learned this in Calc 3, if you took Calc 3 and you learned it in the conservative vector fields and potential functions. So those were the words used. And we're not going to have the same approach, but it's exactly the same thing. So in Calc 3, we said that field is something that you can measure. You can measure electrical field, gravitational field, magnetic field. You can measure the speed of the current of the water in the ocean or the river. You can measure the speed of the wind. You can measure the speed inside a tornado or the hurricane. And those wind speeds are actually measurements of what we call the field, which is a lot of vectors moving right in the, well, vectors is what we perceive, mathematical construct. They don't actually exist. We use them to measure and explain mathematically, the motion of the particles, which are, the air molecules and water molecules and whatever. You can also, do the flow of traffic and all of that stuff. You can do it in the same stuff. So when you deal with the field, you measure the field, and when you measure the field, you can use this procedure to make what you call potential function. Now, potential function is actual algebraic formula or the equation which you use to that equation to describe the phenomenon, right? So once you understand the equation, you understand how the wind behaves, you understand how the water behaves, the traffic flow, like literally anything that you want to, you can understand the way it behaves. So now, going from this situation here, you have exact equation is going to be equation of the form m of xy dx plus n xy dy is equal to 0. This is what you would call the differential form, right? So, YouTube is not receiving enough video to maintain streaming. So it looks like that the stream, no, it looks like it's, okay, so YouTube is having issues now. YouTube is having issues. So we have it is what it is. We have a differential here, which is the measurement of the change in x direction. And you have the measurement here, which is the measure of change in the y direction. And then you have the total of that change, right, equaling to 0. Now, the condition for exactness, so this is a big deal over here. That's the equation. And then condition is that partial m partial y is equal to partial n partial x. This is this is what we have for condition. Now, the thing here is that if your condition doesn't hold, then if your condition doesn't hold, that means that your equation that you're observing is not exact and you cannot use this method. So please make the note of that. Must hold for equation to be exact. If not, we must use another method. So that's what we have. So that's what we have, right? And this is actually going to involve partial derivatives, right? From Calc 3, which is why I asked you, this is the second time we're using partial derivatives. I mean, we are done with using partial derivatives for, I think, for the whole course, but you know, you need to know them from this. And you have my lectures, but you also have like 10,000 other lectures on YouTube for partial derivatives. I'm going to do a whole bunch of examples here, but you know, just to be on the safe side, try to find as many of these as you can possibly, as you possibly can. So let's see the example and the way. There is no theory here. There's only a procedure on how to solve this, and that's going to be 4x minus y dx. This is problem 32. Again, you read the examples in the book. Plus 6y minus x dy equal to 0. If you consider your equation and the condition which you must check first, you see that immediately that this part is your m and this part over here is your n. Right? Those are the two. And what you do is you take the partial derivatives in respect to y for m and in respect to x to n and check if those two are equal. If they are, we can go and solve the problem. So I have my partial m, which means I need to find partial m, partial y. And that's going to be -1. Because when I'm taking the derivative in respect to y of this, there is no y in the first term. It's all in respect to x, which means that the derivative is 0 because it's all constants in the eyes of the derivative. There is no variable in the entire term because my variable is y. There is no y in the first term, therefore partial derivative in respect to y for the first term is just 0. Now the derivative of y in respect to y is 1, and then you have a minus, right? So it's -1. And the -1 is the partial derivative, which is dm dy. Now we are going to do dn, or partial n, partial x, and it's the same deal. Your variable now is x. The first term has no x inside, so you know that's just going to be 0. And then the derivative of -x in respect to x is -1. -1 equals -1. So in this case, you have correct, right? Condition is satisfied, condition is passed, which means that we are we have the exact equation, which means that we can go on and do the procedure. Okay, now what's the procedure here in blood? Procedure. So procedure is you integrate m in respect to 2x, and you get some function over here, call it, I don't know, f star, whatever, and then you will take the partial derivative of f star in respect to y and equal that to n, and then go from there to solve it. So that's the procedure, right? You integrate m in respect to x, and then you take the partial derivative in respect to y and equal it to n, because n would be then considered that. So let's go. Integral, integral. Now m was 4x minus y, and that's going to be integrated in respect to x. So that's going to be 2x squared minus yx. And here is the new feature. Please pay attention to this one. Plus the constant in respect to y. It's a function now. It's not a constant. It's a whole function. Now, this could be a constant, could be 3, but it also could be 3y squared. The reason why this must be a function now is because you are actually doing the partial differentiation, partial integration here. You're integrating in respect to one variable where there is another variable y. And think about this. If you are to check your work and take the derivative of this, if this was, 10y squared, when you take the derivative of it, it still would be 0 and it would still fit here. So this could be a function of y. We don't have any information about it now. Therefore, I have to put that as some kind of a derivative, so some kind of function in respect to y. Now, it could be a number or it could be a function of y. It could be ln y, could be e to the y, could be sine y, could be y cubed, y squared, or could be just 10, right? Could be anything. All right, so now the next step in the procedure here is to take the partial derivative in respect to y of what we just had and equal it to n, which is up there, 6y minus x. So when I take the partial derivative here, that's going to be 0. This is going to give me negative x, and this is just going to be c prime of y equal to 6y minus x. So what I'm getting here is that negative x minus c prime of y is equal to 6y minus x. And cancel x's on both sides, right? You add x and they're just gone. And look what you get. You get that c prime of y is equal to negative 6y, right? Move this negative to the other side. Guys, if we didn't have that c of y, we would completely miss this part of the answer, right? So we have to put that c of y there and then follow the algebra wherever it goes from that point. So now I'm going to put here, integrate both sides. This is going to give me c of y on the left, and on the right, negative 3y squared plus, you can say constant k. It's all right, constant k. Look, if we go back, this was your answer. You just needed this piece of the puzzle, and now we found it. So what is the answer now? Solution. F of xy, it's an implicit solution, f of xy is equal to the solution that we have up there, 2x minus yx, 2x minus, you can say xy, and then minus 3y squared plus k. And we don't have initial conditions, so we're done here. Right? We can't compute k. It's a general solution. But it's implicit, right? You don't have this as y equal everything else. Now, MyMATLAB, we don't need to be dramatic there. MyMATLAB might be taking the answer as 2x minus xy minus 3y squared equals to k or c, whatever. So that's also an implicit solution. Or 2x minus xy minus 3y squared minus k equal to, plus k equal to 0. Remember, when you move k to the other side, it doesn't, that minus sign gets absorbed because it's a constant. So try both of these, right? If it tells you that it's wrong, plugging in one of them, again, it's a new software for this course, so they don't have all of the possible forms of the solution programmed in yet. So, it might take both, but it could take only one of them. So try, right, the exam, you can also leave this one. But then for my MATLAB, you know, this could be an issue. So equaling that to 0 because there is a k in there would be fine. This is a calc3 way to write this anyway, because you say potential function phi of xy if you took calc3. So you know, for my MATLAB and your homework, it might be good for you guys to learn which one of the two answers, right? And for your exam, you know, I'm going to accept any of the three answers, obviously, because I'm not programmed. So, you know, I can jump between these easily. That's exact equations. Let's go do another example. So you have more of these. And again, if you want to learn and see even more examples, because Calc3 is the same procedure, same everything, just, you know, they talk about potential function and vector fields and so on in addition to that. Look for 17.3 in Calc3. 17.3 Calc3, right? My YouTube lectures will have a whole bunch of these solved, and you will also have a three-dimensional ones there as well. These are all 2D in this course, so you know there's less computation here. Let's try another one. For instance, let's keep from polynomial into rational and log functions. 35. Yes.
Professor, was this 2x or 2x squared? Just I missed
2x.
something.
2x squared, yes.
Squared, right?
Yeah, I was just testing everyone, and you just passed the test, and everyone else is terrible. Yes, you're right. Good. All right, good. Yes, it's x squared. Thank you. So, 35, we have x cubed plus y over x dx plus y squared plus ln x dy equal to 0. You have to check condition for exactness, because if you don't, you are not going to get the right. If it's not exact, you're not going to detect that and then try to solve it and get the garbage answer. So we have to go partial m, partial y. This is your m. This is your n. Right? Alphabet, m goes before n. Good. So m with y and n with x. So partial derivative in respect to y. Okay, so this could be a little bit confusing, but please understand that y over x is equal to 1 over x times y. That's a constant for y variable, and y is your variable. So when I am taking the partial derivative of this, I copy the constant and then take derivative of y, which is 1, so the whole thing is just 1 over x. So that's the partial derivative situation. It's not implicit, it's not quotient rule or anything like that, because y is its own variable and x is it's not y is a function of x anymore. Now you have x's and y's separate. So when you take your derivative, anything that is not a y is a constant, whether it's a letter or a number. Anything other than y is a constant if you're taking derivative in respect to y. So the way you would take the derivative of 6y would be you copy 6 and then derivative of y is 1. That's the way you would take the derivative of 6y. So 1 over x times y will behave the same way, because x is considered to be a variable, right? X is considered to be a constant. Y is considered to be a variable. So when I get rid of all of this, and you can go back in the YouTube video and watch it again, I'm going to now take the partial n partial x, which is going to be just 1 over x because there is no x in here, so derivative is 0, and the derivative of ln x is just 1 over x, and we have a condition is constant because I have the 1 over x is equal to 1 over x. And because 1 over x is equal to 1 over x, then the condition is satisfied and I can go and do the procedure. So the procedure is we integrate x cubed plus y over x dx, and that immediately gives us the solution for the problem, just one step. But it has that y, c of y, which you have to figure out down the line. So when I integrate here, I get x to the 4 over 4 plus, and now the y is the constant, so I am integrating 1 over x. The integral of 1 over x is ln absolute x, right? So this becomes y ln absolute x plus c of y. Again, y over x is the same as y times 1 over x. Since I am integrating this in respect to dx, that's a variable, that's a constant. I copy the constant and I integrate this as the ln absolute x, and then plus c, but remember it has to be in terms of y. So that's how we get that second term that is usually very confusing for people who didn't take Calc 3, right? So you have to be a little bit careful about these things. All right, cool. That's gone. So guys, this is already some kind of a partial solution here, right? Some kind of a partial solution where I need to now take the partial derivative in respect to y of this mess. And equal that to n. So that's the next part. Partial derivative of x to the 4 over 4 is just 0 plus. Now I'm taking the derivative in respect to y, meaning y is the variable, ln x is constant. So copy the constant and then times the derivative of y, which is 1, and then plus c prime of y is equal to y squared plus ln x, which is our n, right? So that's our n. So I have ln x plus c prime of y equal to y squared plus ln x. Ln x will cancel on both sides, and you have your c prime equal y squared. When you integrate, right, you get c of y is equal to y cubed over 3 plus some constant k. I'm using k. You can use L. You can use whatever you like. Capital A, doesn't matter. Because c was already taken, even though it was a function before, it's a very slight, move from cy to c, right? So I don't want those to be confused. So I'm going to now state that this is just a constant. This is a number. It cannot be a function. It cannot be anything. This is your Calc 1 integral, right? Where you're just integrating in respect to y. And, x squared is x cubed over 3 plus c. Now you're getting y cubed over 3 plus k. It's absolutely the same basic Calc 1 integral. And now we're ready to write our solution, right? Our f of xy is equal to our good old function from above, x to the 4 over 4 plus y ln x plus y cubed over 3 plus k. And that's our solution for this exact equation. It's, it's a solution. And you can write it also as write this part equal to k. Again, please research, be careful what is the way that MyMATLAB wants you to plug in the answer. Before we hit the break, I have one more example to work out. And I just want to point out something that if you see that the problem can be solved by separation of variables, you should do it. Because it's, you know, it is not always, right, something that you should immediately, you know, go and say, okay, this is exact equation. You try all the methods, and you want to try the easiest method first, obviously, separation of variables. Because why would you mess with integrating factor, with the integration and exponential and that backwards product rule? Substitution, which we saw that it's absolute nightmare. Then this has, you know, quite a bit of steps and stuff. If you can just simply solve it by exact equations. Now, I want to present one more problem. Just give me 1 second. I think I got this right. So here it, oops. There we go. I can do y prime, it's easier. Y prime is equal to minus 2x minus 3y divided by 3x plus 2y. So you can't separate these variables because you can't get x's and y's away from each other so that you can put them on two different sides. There is literally nothing you can do to do this, right? So now we are supposed to figure out, you know, what else can we do? Can we use substitution? Can we use integrating factor, right? So there's all of these things that are popping in and out of existence until you say, is this exact equation? And then someone might go, it doesn't look like it is. Yeah, but sometimes things don't look particular way and yet they are that way, right? So what do? You write this as dy over dx is equal to negative 2x minus 3y. This is you trying a method that doesn't look like it is the proper appropriate method, but you are transforming the problem into the form, hoping it would work out. Now, you know that you are supposed to cross multiply to get these dx and dy there, so it's going to be 3x plus 2y dy, and then negative, factor out negative, and you have 2x plus 3y dx. So you factor the negative and at the same time do that and just move this whole term that way. So it's going to be 2x plus 3y dx plus the 3x plus 2y that was already there equal to 0. Now, literally any equation can be transformed into exact form. But is it going to pass the exact condition? So I can go to any equation we had prior to this point in time, any, and transform it into this. But only exact equations pass the condition for exactness. So if this, then exact, okay? So any equation can be transformed just using basic algebra. And then once you transform it, you can once you transform it, That's it. Good. So let's check. Partial derivative of m in respect to y is 3. There is no x in the first, well, there is no y in the first one, so derivative is 0, and derivative of 3y in respect to y is 3. Second one is partial n partial x, and it's also 3. It's exact. Woohoo! So we start with a problem that doesn't look like exact equation because you are programmed by the formula, right? That it has to look like this. But things could be shoveled around, right? With algebra, you can change them into other forms. What's most important part is for a condition for exactness to hold. So now that we have that, we integrate 2x plus 3y in respect to dx, get x squared plus 3 halves y, xy, no, 3xy, sorry. We can't integrate, there is no x in there. Plus c of y. And that's already our partial solution. Like if you get up to here, you got 6 out of 10 points on your exam. And then now you figure out what c of y is by partial derivative in respect to y of x squared plus 3xy plus c of y, and equal that to n. So first term is done, second term is 3x plus c prime of y equals, and my n was 3x plus 2y, I hope, because 3x would drop, and I have my c prime of y is equal to 2y. Hit both sides with the integral, and what you get here is c of y equals y squared plus constant k. So the answer, the function we are looking for, is x squared plus 3xy plus y squared plus k. Or MML form, x squared plus 3xy plus y squared equal k. Depends again, or maybe it's going to be plus k equals to 0. So try whatever form the homework accepts, right? Because you need those questions. You need minimum of 5 questions, right? Correctly, so you can score your 100 for the exam. And that's exact equations, which ends chapter 1. So we are going to have an exam after chapter 2, I think, or maybe even a little bit further than that, maybe half, because we have the midterm is the first exam. We go quite far into differential equation, and then we have after that more exams. So at least the first 2 chapters are on the midterm. So we have to go through to the chapter 2, and the chapter 2 is not that long. It's actually very short because it's 6 sections. I combined the last 3 sections in the one lecture because it's all numerical computation. So we'll see how is that done. We're going to take 5-minute break. So we will resume at 12:05, and we'll go from there. But this is now 1.6 and chapter 1 are officially done, over. So I'll see you all in 5 minutes.